whenever I do that early, people have this idea, oh, well, I'll just flop this one. It's a freebie. I'm going to tell you, don't hurt yourself. I don't know how. I mean, I think there's an attitude, and we all have, that, you want to get away with something, sort of, and don't do that. You're not going to get away with it. It tends to come back and really bite you, especially in this class, because it's so short. I don't know, Frank, I want to tell you this. On OneNote, on Canvas, when they show your grades and they have an estimate, the problem with that is it's not my grading scheme. I show you how much each quiz is worth. What I don't show you is how much the average of all those quizzes is in terms of your grade. And you can get this false confidence if you don't use the grading that I talk about, where I think quizzes are 35 or 35%, the finals 35%, and then the midterm is the remainder. You all follow me on this? Which, if you don't follow that grading scheme and you just look at that and assume it's right, even though you may be doing well on that average, if you can really blow it when you look at the actual way the grade is calculated. So just be careful about that. Just put your grades in an Excel spreadsheet. That's what I tell kids. And that will give you a very accurate rendering because you've got the percentages. And then some people say, well, do you scale the class? I have to say this. 90 or above, you get an A. Right? I'm telling you, you just do 80 and above, you get an A, or a B. 80 to 90, I mean, and so forth down the line, right? Where it gets hard to say for sure is, if you're like at an 88 and you've done very well in the final, I'll put you over to an A. I'm just telling you that. I mean, I can't say exactly the formula I use yet because I don't know how things are going to go. But I can't tell you, if you get like a 48 on the class average and you ask me, am I going to pass? No. I mean, you're like 2 or 3 standard deviations away from the 60 points. Y'all follow me on this class? I'm trying to just level with you guys so that there's no, assumed idea that's wrong. And I've heard of different professors I heard of a sheer scaling like 35 points or something like this. All right, I mean, I don't know how that can happen, but I'm not going to, just so you know. All right, that said, back to this. I left my book too. I think my book's in my office upstairs. But I wanted to go through these problems today in section 6.3 and go through 6.4. And the reason I'm saying is these are a little different and more complicated if you look at it. Now, the very first problem I want to do is 6-3.2. How many tried that problem? One? Anybody else? All right, this one is, I mean, what did you think of it? Don't you think 6.3 and 6-3.2, 6-3.3, they're much more complicated and they're, conceptually they can fool you. When you get a problem like this on a test, this is where you really get hurt. If you haven't really spent time thinking about it. Okay, you have access to that. Alex. So this is, give me 1 second. I'll ask you on this question, is there something going on? Why? You got a test or something? Okay. Well,
Drew thinks like tons of people dropped or something. I don't know if that doesn't make sense to me.
they could have, but I mean, there's some very good students that are on here too. Anything can happen. It's the summer. And, all right, this is 6-3.2. It's a problem. It's a good one. So go ahead with this.
Random process has sample functions of the form x of t is equal to y cosine omega naught t plus beta.
Plus theta, right?
Yeah.
Okay, go ahead.
In which y, y, omega naught, and theta are statistically independent random variables.
Y, omega naught, and theta are all statistically independent, which is very important. Go ahead.
The assume that y has a mean value of 3 and a variance of 9. That theta is uniformly distributed from negative pi to pi.
F of theta means 1 over 2 pi from minus pi, okay?
And then omega naught is uniformly distributed from negative 6 to positive 6.
All right, so we've got, they give you basically information about the distributions of these two functions, omega naught and theta, but for y, they just tell you what the standard deviation is, I'm sorry, what the variance is and what the average is. Now, I'm going to start just by, when you take one look at that for a second, here's something I'm going to tell you now. I read them down clearly, so I won't make a mistake later on in the problem. This one, when you look at this automatically tells me the mean squared value of y. So if you wanted the mean squared value, that's sigma y squared plus the mean value of y squared. And if you look at that, that's going to be 9 plus 3 squared is 9, so it would be 18. We're going to take care of that right off the bat. I think you all follow me on that, right? Now these two, something to just note about this, because these two are uniform distributions, I put down the density function. It's basically 1 over the spread if they're uniform. But the mean value of both of these is 0. And theta mean is 0 as well, which is important. Okay, now we get with the problem. He gives us this function, it's a function of time, and you'll notice that the only place time appears is right there. Now, for part A, we're going to do this. I want to go through this one because it really showcases a lot of the stuff that's important. What's the first question? By the way, the solutions manual, the one that I put in the very first OneNote section, if you look on that, it has a wrong answer for the first part. It says it is wide sense stationary. It's not. But you can't see it just looking. You've got to actually prove it. It is not ergodic either, and we'll see why in a second. But all right, so what's the first question?
Is this process stationary? Is it ergodic?
All right. You can't answer that without getting the autocorrelation function. And I'm going to ask this. So what is the definition of ergodic? Think about it. It's basically that what? If we took the density function and we calculated the mean of, say, if we're talking about x, right? If you take the density function of x to calculate, it's say its mean or its standard deviation, it would be the same thing as taking the time average of that function. The two would give you the same mean. Follow me, class? The statistics can be found by either time averaging or doing the density function integral, either one. That's the sort of the definition for ergodic. Wide sense stationary means that the autocorrelation function is only going to be a function of the difference T1 and T2, not the actual location of T1 and T2. Follow me? All right, now, we can talk about, the real thing is when we get the autocorrelation function, we can answer the second part if it is stationary or not. For the ergodic part, we need the density, we need to calculate this stuff. You all follow me on this? So that, I'm going to leave that one go and go to the next part. You looked at this, right? This one. Do you notice how that basically you can't answer that part without the latter parts of the question? Answer, go ahead.
Find the mean and mean square value of the process.
All right, so for part B, we need the mean value of this process right here. And to calculate the mean value, we'll do it first. We're going to go ahead and use the density function method. Basically, we're going to do it with density functions because if we're going to first calculate that, follow me on this, class? All right, so to calculate the mean, I'll put it up here. The mean value of x, expected value of x and t here, That's the expected value of this process, y times cosine of omega t plus theta. And I think y'all agree with this. We're doing this, we're gonna do this using the density functions. Now, because, if you look at this, because y and this function cosine, everything is they're independent random functions. Follow me on this? Because of that, I can say it's really going to be the expected value of y times the expected value of cosine of omega naught t plus theta. And for the expected value of y, that is 3. Y'all follow me on that? And the expected value of the cosine function, well, if you look at this, I guess we can do this in a couple of ways. For the expected value of a cosine function like this, since we have 2 random variables, it would be expected, what is this, a cosine of omega naught t plus theta, and cosine A. I want to check and make sure. You know what? Normally what I would do is this. I don't think the book does it this way. I would expand this. You got cosine A plus B, cosine A, cosine B minus sine A, sine B is not, I believe that's right. Do you remember this class? Do you remember the trig identity things? Cosine A plus cosine B, cosine A minus cosine B. You expand them out to cosine, cosine, sine, sine. Do y'all remember that? Sort of. I don't blame you. If we did that and we got the expected value of each of those, we'd find out basically the same thing I'm going to tell you. If you look at this right here, you want the expected value of it. Well, if we just do the density function of theta, just watch this. So we're going to use, normally you would have to take the expected value of that function with theta and holding omega naught constant plus the expected value of holding theta constant of omega naught. And they both are symmetric from -6 to 6 on one of them and from minus pi to pi on the other. However, if we just take a look at this and we want the expected value, I can prove this. When I'm doing this expected value of this thing, if I can prove it's 0 just for theta, it will be 0 complete. So if I take the expected value of this would be 1 over 2 pi, because the density function goes from minus pi to pi, of minus pi to pi of cosine of omega naught t plus theta, but it's going to be, this is going to be the expected value with respect to theta. Can you all follow me on this, class? Now, anytime you see a trig, I mean, either a sine or a cosine, where you're doing an integration over a period, everybody knows that's, y'all follow me on this? It's 0 always. A sine or cosine, anytime you integrate it over one period, gives you 0, which means that's 0. Now, if that's 0, I got 3 times 0, and that is 0, 2. All right. That was kind of a straightforward one. Follow me? All right, the next part is, you're going to have to, that is what you expect. Is it the mean squared value?
Yeah, mean squared value.
All right, for the mean squared value, do you mind if I just use this right here? Okay, mean squared value is going to be x squared, which means this whole, now I can do this, I can put a squared there and a squared there, because basically, I'm going to separate these two, because this one's actually going to be what? The y squared is independent of this function. They're not statistically dependent. Follow me? And that means I get this right here. I'll step out of your way. Slow down. And then I get this right here. Basically, the y squared and the cosine operator squared, right? Now, on this one, you take a look at this. The expected value of y squared would be, just look. Just take a look. Anybody?
Yes, the 18, right?
18, right. That's 18. One of these marks, actually. Let's leave down. I think this is a losing proposition. Any condition. So this is going to be expected value of that, which is, let's get rid of these. All ones that are bad are going to get, oh. Okay, so like you said, this is 18. Now, if you just take a look at this, whenever you get a cosine squared or a sine squared, you can always break it up and use half-angle formulas. So I know that, I'll put it right here. Cosine squared of theta is equal to 1/2 plus 1/2 cosine of 2 theta. Do y'all remember that? That one is real handy. You'll see both the sine squared and the cosine squared one are real handy. And if you just want to remember one, say you just know the cosine squared one. Well, sine squared is 1 minus cosine squared. Follow me? So you can take 1 minus, if it was a sine squared, 1/2 minus 1/2 cosine 2 theta, and now you have the sine squared one. Y'all agree with this? All right, back to this. Now I need the expected value of 1/2 plus 1/2 cosine of, and here it's going to be 2 omega naught t plus 2 theta. And here. Basically, I need the expected value of 1/2, which would be 1/2, right? So this is going to be 18 times 1/2 plus, and what would be the expected value of this cosine 2 omega naught t plus 2 theta? Think up there. Do y'all see it 0? Because anytime you have, and I have, this is a function of theta, so when I take the expected value of theta, and I integrate over theta, from minus pi to pi is over a period, it's 0. That's the reason. So it's going to be plus 0, or this is going to be simply 9. And I'm almost guaranteeing that's true. Do y'all follow me on this, class? And what's the next part of this problem?
Find out our correlation function.
Okay. I'm listing it there, but I'm doing it over there, so I'm just going to get rid of this. So when we want the autocorrelation function, now, if you're actually, if there's, like, you have to figure out if it's wide sense stationary or not. Now you've got to use the formal definition of the autocorrelation function with T1 and T2. And I'll show you what I mean by that. So for Ry of tau, and really I'm not even going to use tau, I'm going to use T1 and T2. And the reason I'm doing that is because, you know, the focus of this, I'm not focused on this if for whatever reason there's a question about is it or is it not wide sense stationary, this is the way to go. So now we come up here, and what this is really saying is the expected value of y of t times, or T1 times y of T2. This is what we're after. Tau is really going to be equal to T2 minus T1, or T1 minus T2, it doesn't matter. So that's what we're looking for. So this is the expected value of and it would be quantity y times cosine of omega naught t1 plus theta, and it would be times y cosine of omega naught t2 plus theta. Now, the only thing I'm doing is literally taking the definition of x, or I should say x, not y, pardon me. Here, taking the expected value of x at t1 and the expected value of x at t2 from that definition right there. I mean, this is the actual formula that we're trying to figure out the relationship of all this stuff to. So here I can break this out, and I really have the expected value of, I'm going to get y squared, which is nice. And then I have cosine of omega naught t1 plus theta times cosine of omega naught t2 plus theta. And as usual, I can go ahead and say that's the expected value of y squared, which we just got, times the expected value of those cosine functions. All right, y'all agree with that? We got the expected value of y squared from the earlier part. We just did that. I think it's 9, correct, class?
Mm-hmm.
It was 9, so we got that one. What about this one? And here, this is where trig identities come in, because now there's a bunch of ways you could do this. You could take cosine AB, expand the first one, and then take cosine AB here, expand it, and then take the averages of all this. I'm trying to see, the way I did it was, or the way I should say, I put in the solutions on OneNote. The way they did it, they used this identity, or this is one of them. I probably wouldn't have used this one. Cosine A times cosine B is equal to cosine of A plus B over 2 plus cosine of A minus B over 2. I believe that's that is the one. Now, getting back to this thing, and I'm gonna go right here. I'm gonna take, this is 18, so we know we got 18. Now for this one, when I look at A and B, this is my A, and this is my B for that formula. And if you look at that, first part is going to be A minus B, so that's going to be times the expected value of cosine, and that would be omega naught T1 minus T2 over 2 plus, and then down here I'll write cosine of, and it would be omega naught T1 plus T2 plus 2 theta. This whole thing is over 2. Y'all follow me, class? I'm just taking that definition of cosine A, cosine A times cosine B is cosine A plus B over 2 plus cosine A minus B over 2. and I'm replacing the A and B with what I've showed you there, and we get this, y'all with me? But I still need the expected value of this whole thing as well. So if you look at this, just for a second, just be attentive to this one. You see how this part is T1 minus T2? That checks the box of tau that we want, only a difference of the two, right? But if you look at the next one, this is tau 1 plus T2. Now, just looking at that with nothing else, that tells me it is not going to be wide sense stationary because it is a function of T1 minus T2, just looking at it. Now, there is one exception. If, and that would be, if you look at these things, if this is averaged to 0, then it is not a function. The autocorrelation is not a function. So anyway, we're going to keep going on this one. And if you look at this, now I've got to get the expected value of these things. Let me ask you this. What's the expected value of this?
Is that one also 0?
And the reason is because it's got a theta inside the argument. And we know theta is uniformly distributed from minus pi to pi. Follow me? When you integrate this, it is a cosine function, it will average out to 0. This part, if you look at this, we'll be integrating omega naught. This is a little trickier. I want to show you this. And it would be an integration of omega naught. Now I'm going to do something, so I'm going to put this down here and really try to make a point. 18, and it's going to be times the expected value of, I can take the 2 out of the front, by the way, so I'll take 18 over 2 is not. Expected value of cosine of omega naught, and here I'm going to put tau here. So now I'm going to define tau as T1 minus T2, just because it'll make my life a little easier. And this is something you can get in trouble for if you're not careful. If you look at this, the expected value of this right here, well, that's a cosine function, right? That's an even function. And we got omega naught, but omega naught, if you look at this thing right here, it's distributed from minus 6 to plus 6. Do you all follow me? Right here. So when we get that expected value, and I'll do it over here, the expected value of cosine of omega naught tau right here, and this is going to be with respect to omega, this is going to be equal to the integral from minus 6 to 6 of cosine of omega naught tau, it would be d omega naught. Y'all agree with that? Now, this is an integral with omega naught. Integral of a cosine like integral of cosine ax, or a times x dx. That's going to be 1 over a, and it would be sine of ax, and then you evaluate. Do y'all follow me? So this is going to end up being 1 over tau, and then it's going to be the sine of omega naught tau evaluated from minus 6 to 6. This is kind of it's more involved than usual. Do that. Now, I can take a look at that, and that's going to be 1 over tau. And here, I'm going to have the sine of 6 tau minus the sine of minus 6 tau. You can see right here, I'm putting in the actual limits. But because sine is an odd function, I know the sine of x is minus the sine of minus x. So I can take this and just make it plus sine 6t, or then I get 2 over tau times the sine of 6 tau. If you take one look at this though, if you think about that, if it would be over a period, then it would be 0. Do y'all follow me? But it's not. That's the kicker. He didn't give us, and remember, tau itself, we don't know what tau is. It could be 0, it could be anything. Now if you take a look at this, that means this is going to be 18 over 2, or 9, and it's going to be 9 times 2, and then it's going to be the sine of 6 tau over and tau, and did I forget something here? Oh, I forgot the half angle, I think. Where is that? Hold on. Okay. Something doesn't look right about this, but let's check. What did I forget? Density functions. The density function of this is 1/12. My pad on this one, sorry. So that would be a 12. That would be a 12. That would be a 12 here. When I'm taking the expected value, I have to take the density function times the actual value of we want the expected value. Follow me on this class? I'm sorry. Right here, it's not just the integral from -6 to 6 of cosine. I have to have the density function right there in front of it. You know, whenever you want the average value of any function, f of x, it's the density function of that function times f of x integrated over the domain. And then when that's done, that would be this over 12. So what do I end up getting? I get the sine of 6 tau or 3 over 2 tau. And that would be the autocorrelation function. I said before, it wasn't a line sense stationary. This is actually, when I look at this, that is only a function of the time difference, so I guess it is Lie-sense stationary. I was wrong about that, but it's not ergodic. But that's the way you'd get that. Follow me, class? Now that's tricky. And one of the thoughts that should be going through your mind right now is, would I provide trig identities if needed? And I will on a test. Because you're going to, when you get through communications, you'll know them probably by heart, because you have to use these things continually, all the trig identities. All right, that was, is that right, by the way? I think it is.
Yeah, that's what you have.
The autocorrelation function. Then I did this long pad there. Then what's the last one?
That was the last one.
All right, but that's a much more involved problem than you're probably used to, but it's a very good problem. I wouldn't probably ask, is it ergodic or stationary, but I could ask everything else. Mean value, mean squared value, the autocorrelation, or cross-correlation function, autocorrelation.
How did you say you could tell if it was ergodic or not?
Well, remember, if you took the time averages of these things, are they the actual same thing as the density function averages, and they will not be. But when you look on OneNote, I'm not sure exactly what was put down explicitly about this, but they calculate and compare, and they're not, I believe. Isn't that right?
That's what I remember.
That's how you do it. Now, I'm not going to test you asking you questions about is it ergodic and is it wide sense stationary. The reason I'm not going to do this is, frankly, the amount of time for the mathematics is usually significant just to ask that question if you want to do a good job on it. And it's more of a mathematical proof than it is like an application to an engineering problem. Even though at the higher levels, I mean, if you're in communication theory, information theory, you're going to have to probably do a lot of that sorting through to see if data is in fact wide sense stationary. But here's how they do it in the real world, from what I gather. I've never had to do that, by the way. They have a record, a data record of anything. Do you think of any events out there? We talked about ion densities, but they have a data record. And what they'll do is they'll take, if they know the physics and they notice statistically like what the density function distributions are, they'll calculate, let's say for that function, you've got three variables. They'll calculate the mean and average and variance using just the density functions. Then they'll go through the time record and they'll calculate basically the autocorrelation function using that time record, x of t minus tau. You have to do this for many, many different values of tau. And then we take the integral of that thing from minus t to plus t times divided by 1 over 2t. You're going to see this more in a second when we get into cross correlation. And take the limit as capital T goes to infinity. That would be a time average. And they have to increment tau. Remember that. You got to do this integral over and over and over again. And if the two are the same, the autocorrelation function you find from the actual statistics, and they agree with what you find from the data, then it checks the boxes. But you can do that with a computer program very quickly, usually. The noise even cancels out, which is nice. We'll see that hopefully later today. All right, that's 6.3, and then I'll move into the other stuff that I want to cover. This one is a pretty good problem, too. I like these two problems. This one,
A stationary random process has an autocorrelation function of the form Rx of tau is equal to 100 e to the minus tau squared times cosine 2 pi tau plus 10 cosine 6 pi tau plus 36.
plus what?
36.
And, okay, what do they want to know?
Find the mean value, mean square value, and the variance of this process.
We'll do these. I don't think I need to write them out. I'm going to ask. Now, these are the kind of questions that on a quiz or test, you should be able to, this part right here should be a no-brainer. It should be almost instinctive. If I wanted the average value of that, do you remember how to get it? Remember, that's an autocorrelation. Anyone? Just average value.
You just ignore the cosine terms.
What?
You ignore the cosine terms.
Well, that's a good way to put it, but remember, we want to find the DC value. Remember, for all this stuff, when we're talking about, I'll try to draw it here. If this is an autocorrelation function, I'll call it Rx of tau, and this is tau. I'm gonna just sketch one. Anytime you get something like this part right here is really gonna be the mean value squared, follow me? It's the constant term. If you look over here, 36 is the constant term, follow me? So if that's if that's the mean squared, the mean value here would be plus or minus 6. Do y'all follow me? Just the square root of 36. Good with that? Now, how do I get the mean squared value? Do you remember how you get that? Anyone?
Set the limit as tau goes to 0.
Yeah, you're right, but think about this in general. Rx of tau is the expected value of x of t times x of t plus tau, right? Now, if you let tau go to 0, or you get Rx of tau, that's the expected value of x of t squared, isn't it? And that's the very definition of the mean squared value. So when tau equals 0, what's this going to be? The mean squared value. Just take a look. What's cosine of 0? Cosine of 0? 1. Cosine of 0 is 1. So it's going to be equal to 100, because e to the 0 is going to be 1, plus 10 plus 36, or it's 146. You agree with that? Straight, right? How do you get the variance? Mean squared value minus the mean value squared. Does everybody agree with that? And that's going to be, you might as well tell me what it is. So I got 140, actually, I think I can do this one. 146 minus 36, right? And that's going to be 110. That's not very difficult. Those should be just straightforward. Not much angst from you on that one. Y'all agree with that? All right, part B. Where is that? Part B for this one is,
What discrete frequency components are present?
all right, and I got a comment about this. So look at this, what discrete frequency components? It's almost everybody would take a look at this. This one really doesn't count, and here's why. Because as tau gets larger and larger, this thing goes to 0. You with me? I'm not going to hold you for that one. You all agree with this? Now this one is persistent. It carries on regardless of how large tau is. It's still oscillating. So this, omega naught, would be 6 pi. If you divide 6 pi by 2 pi, you get the frequency, right? And that's going to be 3 hertz. Now, what the book will say too is, well, that one persists too, but that would be at 0 hertz. I don't consider 0 hertz something I worry about, because that is the DC term. Like a DC term implies no frequency, a constant. Follow me on that one? So I say 3 hertz. I think in the book, in the solutions manual, they'll have 0 hertz. I'm not going to ask them. And they don't go over here and have 2 pi by 2 pi, or 1 hertz, because this one just dies off. It's gone. I think that's the right answer, isn't it? All right, now, what's part C for this one?
Find the smallest value of tau for which the random variables x and t plus tau are uncorrelated.
Now, I'm going to tell you this right now. This one is tricky. Here's what he meant to ask you, and it's legitimate. He meant to say, what is the value of what is the value of tau that makes that 0? That's what he's asking. If you look at this thing, if I wanted to know when Rx of tau is 0 and you solve for tau, there's no easy way to do that. That's a transcendental equation. You would have to iteratively solve that. You all follow me? But a more appropriate definition, I think I put that on the OneNote notes on this one, the solution. whenever you're talking about, and it said uncorrelated, right? Now, uncorrelated doesn't mean the values can't be non-zero. This is the problem with the two functions. So if you want any variables that are uncorrelated, it means this is the definition, the expected value of x minus, and this would be x bar, times the second function, y minus y bar, are 0. Now, if you look at this, our first function is x of t, so we want the expected value of, here it would be x times, and I'm going to say this, it would be t minus x bar. I'm going to leave it like that because x bar won't change. But here, the second function would be x of t plus tau minus x bar. I put that in there. This is the definition of the covariance of x of t and x of t plus tau. Y'all follow me on this? By the way, if our x of tau is 0, it is uncorrelated. But there can be another value that it would be uncorrelated with. Now, do y'all remember what we used to do is we'd say the covariance, we had this, and then we divide the first term by sigma of the first function and divide the second term by sigma of the second function. And then when you do all that, I mean, you remember the correlation coefficient was the expected value of like x times y minus x bar times y bar over, and then you had 2 sigma x, sigma y. Do y'all remember that stuff from chapter 2, I think, or 3? I don't remember which chapter. I think it was 3. All right. Well, here, we're not getting a correlation coefficient, we're getting the covariance, because the covariance is the top part of that. But if it's 0, the correlation coefficient is 0. Now, if you look at this right here, this is going to be really the expected value of x of t times x of t plus tau, and it's going to be minus the expected value of x times the expected value of x. And that's just because these two are constants and when they're multiplied together. But at the end of the day, when you do this, you're going to have, I'm sorry, I'll just be sure about this. That's going to be autocorrelation minus plus. Yeah, it's minus that. And here, you'll notice that's the definition of the autocorrelation function. Minus, and this is the mean value squared. And what he's asking is for the process to be uncorrelated, they want the value of tau, so this is true. Can y'all follow the logic on this? All right. The covariance matrix, I'm sorry, if we just had this, right, and set it equal to 0, right, that would, and that's basically setting this term equal to 0. Yeah, they are uncorrelated at that point, by definition, but there can be another value even closer, or I should say a smaller value, that by definition would mean they're uncorrelated. Now, if you look here, this is really just removing the 36. And I want to tell you one thing. That constant term will cause a lot of trouble with calculations if you're doing an iterative approach, because this thing's this thing's just dying out real fast, but it starts at 100. This thing's got it's got a slower rate of change than this e to the minus tau squared. But when you put in a constant, fairly large constant to iterate, it gets into the noise of the machine sometimes. So what you're really saying here, it's going to be 100 e to the minus tau squared cosine of 2 pi tau plus, and it's 10, 10 cosine of 6 pi tau equals 0. I'm not going to ask you to solve these things iteratively, but that would be the one you would be the closest or the smallest value. And for that one, would you do an iterative solution? Or were you trying that, or, no? Did you try it or on this one? Pain. I'm looking for where. I didn't even put the answer down, but it should be on OneNote if you look for this. Anybody looking at the OneNote? Isn't that on OneNote for tau? I know Solution Manuals has a value, they just said Rx of tau equal to 0, and they solve for it. It's iterative no matter what you do. But this is actually the smallest value, and I think it's like 0.178 or
It
something.
says 1/4,
What?
1/4 for tau.
What, say, 1.4?
1/4, 0.2.
Oh, well, yeah, that sounds right. Tau be equal to about 1/4. And the logical thing is, am I gonna ask you to solve something like that in a quiz or test? No. But I think your calculators, or you can write a computer program, you can just use MATLAB, it does the solvers, and they'll find all the reads for this. Anyway, that's that problem. Now, after that, okay. So there's sections on PowerPoint on practically implementing the autocorrelation function. I'm not going to worry about that. When you have digital computers, the fact is, when you get a data record, there are so many different functions available for you. If you have any kind of a data record, you know, it's basically, everything's digital these days. So you've got a digitally sampled data record, and you want the autocorrelation of that data. MATLAB has, I think it's called COR of the data set. It will do it for you, and it will give you basically a whole bunch. It's not going to be a closed form function, but what it'll do is give you values. If you tell it a value of tau, if you want to plot Rx versus tau, it'll give you the point by point. It's almost instantaneous these days how fast they do it. Now, I use this stuff in Radar. And what I wanted to do, before I get into, I have Radar problems and stuff. I want to just start the PowerPoint. We'll talk about some things. We'll go through some of the problems, but section 4, I'm going to move through. What I really want to do is get to the spectral energy density. One second. And we may have time to do a problem or two. Is this going to be more rain today?
Looked like it outside.
I don't know. I didn't even look. I didn't have, frankly, interest in doing it. Oh, this one. Yeah. It's not right there. When's your final in email?
We got test 3 the last day of class, and then the final, I think, what is it, August 6th or 7th?
It's that Wednesday.
And our final is?
Friday.
All right, so it's August.
August 5th for the EMAG, and then August 7th for ours.
Are they both at 8 a.m.?
The EMAG one's at 10:30.
Is ours at 8?
Yeah.
And, that's it. It says laptop. Okay. I'm gonna get this up. You all have access to these, right? These are good. So I'm gonna show you what we're moving to. Here, we're gonna be going into the second part, which is gonna be the Fourier transform of the autocorrelation, which is very, very important, and I'll get into that later. But if you take a look at this, these are some of the properties. We went through that, we went through that. We just talked about that, literally, that type of problem a second ago. And we did that one. We did that one. All right, now this is one thing I'm going to mention. And by the way, what I'm about to talk about, he's going to present a autocorrelation function that he does not do a mathematical proof for. And I realized why. But here's the deal. This is a binary process. The average value of this binary process is 0 just by inspection. If the probability of being high or the low is the same, then the average value of that function is 0. It has a magnitude A. A is a random variable. Y'all follow me on this class? This gets a little crazy. The pulse width is a random time shift. No, I said the magnitude. But and there's 3 points to this. So it's going to change sign. It possibly can change sign. The way he says it, it changes. It means it goes from up to low, but it's possible it doesn't. You see here, it's going to stay at just the low state at minus A right here. Anyway, this waveform is like a standard digital waveform that people, when you're, anybody here take communications yet? All right. When you take COM, you're going to find out Jitendra Tugnate's going to use something like this, almost identical, I think, to this, to start out when he does digital communications. And if you look at this, the expected value is 0. The mean value of this thing is going to be 0. And he's saying the width is actually a random variable, not the height. But they'll make width and height a random variable at some point. Anyway, what they want is the autocorrelation function of this. And I'm not going to spend much time on this, but when you get the autocorrelation function, what they're really going to say is this. Over this time frame, over a width here of TA, basically the state doesn't change. Y'all follow me on that? So if you started here and you looked at the expected value of the function from here, try to just follow me on this, to here, it would just be A squared. Follow me? It would be, I mean, if you take Rx of tau and the expected value of X times the expected value of X of T plus tau, of T and T plus tau, and you're just over this range, it would be A squared. But watch, because this part of the waveform is uncorrelated with the next part, if I take A and I multiply it by, basically you get A squared through here, I'm sorry, you would have A times A, but when all of a sudden your window goes from like here to here, there's going to be an A times minus A out here over this range. Y'all follow me? Like if your width goes from here to here, just bear with me on this one. And you're going to, normally you take the functional down back here and you multiply it by a function where how far that function is from the point you're starting is going to move in this direction, so you get A times minus A when tau is greater than some value. Do you follow me in this class? Now the minus, you're going to have A squared for a certain part you're integrating, and then you're going to have minus A squared subtracting from it. You all follow the thought process of this. If you really want, I'll do the mathematical proof for you in my office. But it is one of these things where you've got that window moving, and when you move the window, if it's for the first part from here to here, if that's the total window, as you move tau through there, it doesn't matter. Do you all follow me? Now when the window is from here to here, all of a sudden I move here, I got the A squared, but then I have A times minus A squared in subtracting from that value. And there's going to come a point when you're halfway between here and here, basically from the high point to the low point, it goes to 0. And if you go beyond TA, they're uncorrelated, so it's I don't want to spend way too much time on this. It's a mental challenge to look at what he said in the book and figure it out. But if you actually, I wrote out the mathematics for this, it will work. You can't convince yourself, but it's kind of irritating. And at the end of the day, here's what you're going to get. you're gonna see the autocorrelation function of this is gonna be a squared 1 minus tau over t naught. And it looks like this. You'll notice the total width of this is real important to see, is 2 tau, or 2 TA, pardon. TA is the interval where it's actually correlated. Anything wider than that, you're uncorrelated. So, and it makes sense. It starts at a squared when there is no time difference. That makes absolute sense. X of t times x of t is x squared. You're going to get the mean squared value. But then it goes down to 0 at the extremes, at minus TA and at TA. And this has got to be an even function for it to be legit. I'm not going to hold you to any kind of mathematical proof of that, but you should take a look at that and understand it with me. Okay, all right, we know about that. Now, here's where he goes into some practical applications of that. And he's talking about sampling something at 44.1 kilohertz. That's twice the highest. I mean, you can hear supposedly about 20,000 hertz in the audio range. Anybody ever heard that? Well, you should be at least somewhat familiar with that in the real world. That's about the limit of hearing from people. Dogs can go about 120 hertz, or 120,000 hertz, I think. Some dogs at least. If ours is 20,000 and you want to reproduce sound, you have to, any kind of a sound that's odd that you're listening to, you have to sample it at least twice the highest frequency of interest, or you can't recreate it. That's called really the Nyquist criteria. You all remember that class?
Mm-hmm.
All right, it's very important. So these 44.1 kilohertz, and they got 16-bit A to Ds. Won't get into that part. The signal's either going to be a 1 or a 0 if it's 2 volts or minus 2 volts. Now, we got all the information to create that autocorrelation. If you look at this, the magnitude is 2, therefore the square of that is 4. The actual TA here, if you think about this, he's got 2 channels, there's the 2. 16 is the number of bits. You're going to have to understand that this is like A to D basic information, and then it's going to be the sampling frequency here. Now, 1 over frequency is period. Y'all follow me on this class? And remember, the autocorrelation function, the tau, is actually in seconds. So just bear with me. So I have 1 over 44,000 roughly is going to be a period that has to do with the sampling. But then over that sampling interval, you got to subdivide it, because now you're going to have 16 different bits that are going to be associated with that. Those bits are in the time domain. You know, when you send a bit, it's in the time domain. It's got a certain length. But it's 2 channels, so that's where that 2 comes from. At the end of the day, you get this times tau right here. And you'll notice he just takes 1 over this thing and puts it here instead of dividing by TA. Normally it'd be tau, then it'll be divided by TA. Can you follow me on that? If you remember right here, or right there, it was divided by TA because it was everything they did was frequency samples. Now it's going to be really multiplied by that tau. And these problems, wait a second. We did all these but 3-4. Is 3-4 the one that has the sampling question on it?
I think it's the Fourier transform.
Or just Fourier transform away?
Mm-hmm.
All right. Now, last thing about this that I got to make clear. I'm not going to ask you a problem specifically about this unless I tell you ahead of time it's coming on a test or a quiz. Follow me? Because problems like that, they get tricky real quick. And I think this is in section, is it 6.2? Section 6.2 that has this stuff in it? And look at the problems. All right. This I'm going to move through quickly. How do you measure autocorrelation functions? Well, there's all sorts of tricks. This is one trick, one method. I don't use these things myself anymore, but this is just one way, a approximating, and it's in the digital domain almost always, so he's going to use discrete values of the sample number and the amount of samples, capital N. Don't worry about this, don't worry about this. And then whenever you're talking about sampling and measurements, you're going to have a variance in the autocorrelations function. Remember the variance of the variance from before? Yeah, well, you're going to get that kind of information. Don't worry about it, not here. Want to move through this? I'm not going to ask you homework in 6, 4, 5. If I have any problem, I'll take a look at it and tell you specifically what it is in the answer. This is where I want to get cross-correlation. If you think about this, autocorrelation is just a function correlated with itself. It's x of t and x of t plus tau, or x of t1 averaged against x of t2, right? Now when you get cross-correlation, same exact idea, only one thing. Instead of x here for the second function, you're going to have another, you're not going to have x twice in auto. It's going to be a cross. How well does x correlate with y? And this is the definition. And you'll notice one thing. You can either have x with t1, y with t1 plus tau, or you can have y with t1, x plus, and t1 plus tau. And the real fact is, it doesn't even have to be t1, it can be just t, because at the end of the day, you're going to take time averages of these almost always. And the order is important, but either one of these two defines the process. So this gets a little deep, but just hang with me for a second. Now I got 257 on my watch, 255 on that computer screen, and 256 on my computer, on this one. I'm not sure what the time is. If you have these two processes, it's just a simple example. Can you all see this class? All right, we go ahead and we apply the definition. You'll notice how now he changed T1 to T here. So you just take this, and then you take Y, and you replace the argument with T plus tau. And you'll notice it's here he's going to take the average for this one over theta, because he says theta is uniformly distributed between 0 and 2 pi. Most of the time, these are time averages. Can you all look at this and just, you can see that really what we're going to do, because I have two trig identities right here, we're going to have to find some way of separating these two in terms of trig identities. So this one is going to be cosine times sine. So he's going to have sine A plus B and sine A minus B, I think, identities for this. And that's right here. He gets this, and here's where it gets tricky. If you look here and you see a d theta and a 2 pi, you see two trig functions. There's sort of a knee-jerk approach to this and make it 0, but this is where you actually got to separate them. And you can see that I have sine of 5t plus 5 tau plus 2 theta. That's adding these values, A and B, right here. And then you're going to have subtracting the two values, and the only thing that's left is sine 5 tau and theta. Well, this one integrated with respect to theta is going to be 0, but this one right here is going to remain. So, in fact, he doesn't, he shows it. It's going to be 10 times the sine of 5 tau. And that's it. You can obviously see another trig identities used. So I would provide trig identities, a sheet for you if I'm going to ask you to do this. Some of these get tricky though, I can tell you that. By the way, there's one thing I got to bring up right here. Anything different about that function compared to any other autocorrelation function? It's an odd function for starters, sine, right? Sine of 5 tau. It's also 0 at tau equals 0. That's still allowed. You all follow me in this class? For any time you have cross correlation, You don't have to have a maximum at 0 for tau, I mean, the cross correlation function, and it can be an odd function. All right, this is real important. They have no particular physical significance. They don't represent mean or mean square values, so that's important. This is going to be a symmetric thing. If you take the x argument and switch it with the y argument, it will be something where if you negate the sign, they'll be equal. I shouldn't say symmetric, but they're related. So these are some of, if the processes are independent, then the mean value of x times the mean value of y will be the actual cross correlation functions. If they're uncorrelated, it's basically what they're saying, but they're going to have DC values, average values, that's what you're going to get. Now here's my radar thing, so this is, to me personally, it's important. If you look at this, you transmit a radar signal real simply. Does he show this? Is this thing enlarged too much or something? All right, I don't know why. All right, here's, if you take a look at this, if this is the transmitted signal, and you wait, you know, it's going to hit and bounce back, not scaled appropriately, you're going to get something that's going to have noise. And because of a lot of things going on, you're going to get this waveform distorted. It's going to be something that's got noise on it. You'll notice also there's kind of a triangular shape to this thing. This would be the reflected signal that you captured. Now, I got to tell you, they're only showing like 4 or 5 periods here. Normally, you get a high frequency carrier. This thing is just like a solid piece of black right there, because the high frequency will be, say, a gigahertz, and you're going to have a duration of a millisecond. Think about that. That's 1,000,000 cycles, basically. So this is not drawn to scale. But when you receive it, you're going to have noise, and this is something you can't get rid of. It's there. And the signal itself, you have to take the signal, amplify it one step. Basically, you take the signal, you're going to have something where you're going to amplify it one step as best you can, and then you go from A to D. You sample it, and then you do digital processing. Sometimes you have actually you do have an intermediate frequency mixer, and I'm not going to go there right now. But when you take the autocorrelation function of these two, and this is the real thing that I know, now you get something where the noise basically goes away, because noise is uncorrelated. Wide sense stationary noise is uncorrelated. So this is like a noise filter. It's a drain noise filter. And do you know another term for the autocorrelation function of these two signals that you may have run into? Have you ever heard of matched filter? Anybody? A matched filter or an optimal filter is the one that will give you the highest signal to noise possible of the response. And I'll say more about this. This is my world. But you see, when you look at this, this is real clean and apparent. And the time delay from here to here is actually the round trip time to the target. So if that's the round trip time, divide that by 2 and multiply that by the speed of light, and I've got the distance to the target. That's the idea of radar in a nutshell. There's more to it. I'm going to tell you, let's see. All right. I'm going to ask you to look through those slides, the last part of slides in section 6.7. I'll give you this one problem, 6-7.1. I may give you 1 or 2 other problems related to this stuff. And then, let's see, Friday, there'll be a quiz. And the quiz is going to cover section 6.3 and this that I'm going to give you today. Follow me? So the stuff I covered in class and this. Okay. There's not a whole lot, but it's much more complicated, at least the problem style, in 6-3. At least that's how I felt. Sorry I kept you up. I don't know what I'm going to do, but shortcut. A couple different-
As far as quiz grades go,